You have a multivariate function that is given as the sum of two quadratic forms. Can you rearrange this function in order to only have one quadratic form? The answer is similar to the univariate case where we add two quadratic equations. In this video, we will derive closed form solutions for both the univariate and the multivariate case. Hi, welcome to this new video. The agenda is that we will first derive the univariate case, where we will also look at a simple example, and then we will use this insight in order to derive the multivariate case. Just a general information, both of the equations that we're looking at, or both of the functions that we're looking at, are scalar functions, so the outputs are scalar. They only differ in the number of inputs, whereas in our univariate case we only have one input, and in the multivariate case we have more than one input, a vector valued input. Okay, then let's start with the univariate case. And in the univariate case, our function or quadratic function of x is given as a times in brackets x minus y squared plus b times in brackets x minus z squared. We will first start by evaluating the square on the two brackets, and then we're getting a times x squared minus 2xy plus y squared closing brackets plus b opening brackets x squared minus 2x z plus z squared closing brackets. And then let's multiply the coefficients in the two brackets with their respective brackets, and we're getting ax squared minus 2axy plus ay squared plus bx squared minus 2bxz plus bz squared. And then we can sort for the order of the polynomial, so we can sort for the x with respective exponents. If we collect all the stuff that has to do with x squared, then we get these two terms, and they will be a plus b in brackets times x squared. And then we have the terms that are in x, not in x squared, but just in x. And there we have minus 2 times opening brackets ay plus bz closing brackets x, and the terms that are not in x or that are constant in x are ay squared and bz squared. So let's add them together. So we have ay squared plus bz squared. And we see that we have another quadratic equation, but which is not in this standard form that we are given with. And so let's form it into standard form by completing the square. So this is what we will be doing now. We will complete the square. And for this, let us look at the coefficients. And for this, I will introduce another a, b, c's, and so on, which will be a little bit confusing, but it's just to be consistent with the naming that I introduced in an earlier video. And the coefficient in front of x was called an a, so I will call it an a prime. And the coefficient in front of x was called a b prime, and the constant term was called a c prime. So then we're getting the equation a prime x squared plus b prime x plus c prime. We know we can form this into standard form in a prime opening brackets x minus d closing brackets squared, or d prime, plus an e prime. We know that a prime is a prime, d prime will be minus b prime over 2a prime. These are just results from the video on completing the square. And e prime will be c prime minus b prime squared over 4a prime. Then let's plug in a prime and b prime into and c prime too in our respective formulas in order to get d prime and e prime. So let's start with d prime, and d prime will be, so for b prime we have minus 2ay plus bz, minus in front of the fraction, and we divide by 2 times a plus b in brackets, and then we see the 2 cancels, and the minus also cancels, and then we get the fraction of ay plus bz over a plus b. And for e prime we are getting, so c prime was ay squared plus bz squared. And then let's add this term here. So minus, and b prime was minus 2 opening brackets ay plus bz closing brackets squared over 4 times a plus b in brackets. And then we see if we square 2, then we get 4, and 4 over 4, this cancels. And the minus will be squared, so it is a plus. And then we have another minus, so we keep the minus. Then we have an e prime given as ay squared plus bz squared minus the fraction over a plus b, and in the numerator we have ay plus bz in brackets squared. We can simplify this further by bringing both components on the same denominator and by expanding the square that we have here. And then we have the big denominator a plus b, and we have to multiply this term by a plus b. So we have ay squared in brackets a plus b. We have to multiply this term. It is bz squared, then a plus b. And then we have to evaluate the square, and we're getting a squared y squared plus 2aybz plus b squared z squared, closing bracket. And then let's multiply everything and evaluate the minus, and then we're getting the long fraction over a plus b. And here we have, well, this will be first a squared y squared, then we have ab y squared, then we have b z squared a, and then we have b squared z squared, and then we have minus a squared y squared minus 2aybz, and here we have minus b squared z squared. And then we see that there is something that cancels. There is a squared y squared that cancels, and there's b squared z squared that cancels. And then let's write down what we are left with, the fraction over a plus b, and we have aby squared, and I will just rearrange it a little bit, putting this into the center of this summation. So we have minus aybz plus bz squared a. And we see we have common factors in all of the three summands here, which is ab. So let's bring this out of it, and then we get ab times the fraction over a plus b of y squared minus 2yz plus z squared. And here we see this is nothing else than a binomial formula, which will be y minus z in brackets squared. So we have ab times y minus z in brackets squared over a plus b. And recall, this is nothing else than our e prime. So let's plug this all in. So I will take this equal sign and move it all the way down here, since there's been a really long derivation so far. And then we are getting a prime times in brackets x minus d prime squared plus e prime. And let's plug in what we had. For a prime we had a plus b, so we have a plus b in brackets times x minus, and for d prime we had ay plus bz over a plus b. Then we have closing brackets squared, and for the e prime we have an ab, which is essentially this term here, times y minus z in brackets squared over a plus b. And recall, this is what we got after completing the square for the summation of two quadratic equations or two quadratic forms. And originally we had a times x minus y in brackets squared plus b times x minus z in brackets squared, and we brought it into this form. And let us now identify the coefficients that we wanted to find the closed form solution for, and these are c times x minus d in brackets squared plus e. And here is also what I meant, don't be confused, I used the same naming for the completion here, but I indicated this with the prime. So whenever we are working in the prime, then we are in the completion of the square, and without the prime, we are in our regular variables. And here we see that c is this term, d is this term, and e is this entire term. So let's note this down. C is a plus b, which is our first result. Then we have d is ay plus bz over a plus b. This is our second result. And the last result is ab times y minus z in brackets squared over a plus b. So that was quite tedious, so let us make an example for it. We are looking at the following function that is given as 5 times x minus 2 in brackets squared plus 2 times x minus 2 in brackets squared, and then let's identify the coefficients here. So we have an a of 5, we have an y of 2, we have a b of 2, and we have a z of 2. So let's note this down. A is 5, y is 2, b is 2, and z is also 2. Then let's first calculate the c, and c was a plus b, so it's 5 plus 2, which will be 7. The d was given as ay plus bz over a plus b, so ay is 5 times 2, plus bz is 2 times 2, over a plus b, which is 5 plus 2. Then let's make the calculations, and we're getting 10 plus 4 over 7, which is 14 over 7, and that's essentially 2. Then let's also calculate the e. Here we are having a times b, which is 5 times 2. Then in the numerator we have y minus z, which is 2 minus 2 in brackets squared, over a plus b, which is 5 plus 2. And we see 2 minus 2 is 0, squared is still 0, so our entire e will be 0. And then we can build the expression equivalently as, well, we first have c, which is 7, times x minus d, which is 2, in brackets squared plus 0. I think this is quite obvious, which we would also get if you would just add up these terms, since 5 and 2 are just different coefficients for the same argument here, and we can just simply add them up. With this information in mind, let us now continue to the multivariate case. And recall the multivariate case, that meant that our function is taking more than one input, so a vector valued input, and the function is given as f of vector x as x minus y in brackets transpose, so x vector minus y vector, component-wise subtraction, transpose over matrix A times x minus y vector in brackets, plus x minus z vector in brackets transpose, matrix B times x minus z in brackets. And recall, a quadratic form is outputting a scalar, so what we have here and also here is nothing else than a scalar, because in essence, vector minus vector is still a vector. Vector transpose matrix vector is given as a scalar, because matrix times vector is vector and vector transpose vector is a scalar product, yielding a scalar. Then let's pursue a similar strategy than before by just multiplying out whatever we have here. Then we're getting first x transpose ax, so x transpose ax, and then we're getting x transpose minus y, which will be minus x transpose ay. But later on, we will also be getting minus y transpose ax. And since A is symmetric and also B is symmetric, we can change the vectors to either be multiplied in front of A by vector transpose or after A by just with the vector itself. So in essence, this means we're getting minus 2 times y transpose matrix A times vector x. And then we are left with plus y transpose A y. For the sake of completion, let us note this down, that A and B are symmetric matrices. And symmetric means that A is A transpose and B is B transpose. And we will get a similar expression for the second term, just with B and Z instead. So we have plus x transpose bx minus 2 times z transpose bx plus z transpose bz. Then, similar to before, let's put together all the terms with the highest order in x. For this, we have x transpose ax and we have x transpose bx, which will yield x transpose opening bracket a plus b closing bracket x. For the terms that are just linear in x, we are getting these two, and they are minus 2 opening brackets y transpose a plus z transpose b closing brackets x. And then we have the constant term, which are these two. So we have plus y transpose ay plus z transpose bz. And we can simplify the middle term that is linear in x by putting a transpose outside of the brackets. And because this is essentially equal to ay plus bz set in brackets transpose, because the transposition would also change the order in the matrix multiplication here. And for this, we now have found the coefficients for a general quadratic form. And here we have the matrix A prime, similar to before. And here we then have the vector B prime. And here we have the scalar C. So in essence, we are getting the equation of the format x transpose A prime x plus B prime x, of course B prime transpose because that is the transposition here, plus the scalar C. And just an information, because sometimes people denote the transposition by a prime, but by the prime here I just mean that it is a different A. So this is not transpose. And we can now do the same as we did in the univariate case to complete the square, to bring it into a more nicer format, in the standard format. So what we will be doing now is the completing of the square, or completion of the square. This one is transforming our equation into the following form of an x minus a d vector prime times, or transpose, times a matrix A prime of x minus d prime in brackets transpose plus an e prime, and e prime is just an additional scalar here. And we see then we just have a quadratic form again without the linear term, and this is where we will be heading. And we see a prime is a prime, so we start with writing down the results that we had from the video of the completion of the square, where we had d prime given as minus 1/2 a prime inverse vector b prime. And for the e prime, and of course d prime is a vector, for the e prime we have c prime minus 1/4 b prime transpose, or vector b prime transpose, times matrix A prime times vector B prime. Okay, let us start with the D prime, and for this we will be having minus 1/2, and the A prime was an A plus B, so an A plus B in brackets inverse times the vector B prime, and the vector B prime was what we had here, so we are getting times minus 2 times matrix A y plus matrix B z, closing brackets, and then we see the 2 and the 2 cancels, and the minus cancels. See, this is the same as we had in the univariate case. Then we are left with the expression of A plus B in brackets inverse of AY plus BZ, closing brackets. And that's quite similar to the univariate case. But now it's going to get a little more complicated when we will derive it for the E prime. So the E prime, as said, was given as C prime, and C prime we had as this one here. So we had it as vector Y transpose A Y plus vector Z transpose B Z minus, and now we have the long term, minus 1/4 times opening brackets minus 2 times opening brackets matrix AY plus matrix BZ, then closing brackets transpose, then times matrix A plus matrix B, closing brackets inverse, and then we have minus 2 times the same again, which is AY plus BZ, closing. Then let's look at the 2 and the 4, which will be 2 times 2 is 4/4 will be 1. And the minus cancels, but since we have another minus, we will keep the minus. And then we can again further simplify this equation by evaluating the quadratic form. So in essence, to multiply out what we have here. So we are keeping Y transpose AY plus Z transpose BZ. And we start with minus AY in brackets transpose. And I will already evaluate this, because if I apply the transposition, then this will change the order. So we are getting Y transpose A transpose. But since A is symmetric, A transpose is A. So we are getting minus Y transpose matrix A. And then we have the middle term, which is A plus B in brackets inverse. And then here we have matrix A vector y, and then 2 times the middle term or the mixed term, which is minus 2 times y transpose A times in brackets A plus B to the minus 1 times B set minus, and the last term, which will be in B set. So we have set transpose matrix B, then in brackets A plus B inverse times B set. Okay, then we can bring together some terms that we find in here, and we see that we have y transpose AY, which we essentially also find here, which is y transpose a matrix Y. So let's bring this two terms together, and then we're getting y transpose opening brackets matrix A minus matrix A times A plus B in brackets inverse times A closing brackets y. Then for the next we have the same in set, which is this term here. So we have set transpose B minus A in brackets A plus B inverse B set. And then we are left with the one term which does not match anything here, which is the mixed term of before. And so let's just make this purple and write it down. So it's minus 2 vector y transpose matrix A, then in brackets A plus B inverse times B set. And then we are finished with the simplification. And now it seems kind of confusing that we have this subtraction of two matrices that is within this brackets here. But we can further simplify this. We simplify it by multiplying with an artificial identity. Because if I multiply A with the identity matrix here, it wouldn't change the equation, right? It would be as if we would multiply with 1. So in essence, this would be here the identity. Of course, the identity is given as the inverse of a matrix times the matrix itself. I will select this matrix, so A plus B in brackets, to be the matrix that we want to look at here. And then we're getting the identity to be A plus B in brackets inverse times A plus B. And we will do the same for the B here. And then we can rewrite our equation to get, well, this will be a little lengthy, so we have vector y transpose of matrix A times A plus B in brackets inverse times A plus B minus A times A plus B in brackets inverse times A, closing brackets, and then vector y, plus set transpose matrix B times A plus B in brackets inverse times A plus B, because we did the same thing in this equation here, so maybe also put this here, so it would be the same that we do here, minus B times A plus B in brackets inverse times B, and then closing brackets set. Then we have the last term, which was the mixed term, and we have minus 2 y transpose A times A plus B in brackets inverse times B set. And now you could ask yourself, well, this made our equation more complicated. What is the trick here? And we see that if we multiply this out, so if you multiply A times A plus B in brackets inverse times A, we see that this is the same as we have here. So in essence, the A cancels with this here, and we are left with A times the inverse times B. And the same is true the other way around in our second here. And there we will be having that B cancels with this one. And then we are left with B times the inverse times A. So let us note this down. So we have y transpose times A times A plus B in brackets inverse times B times y, plus the second term, which was set transpose B times A plus B in brackets inverse times matrix A times vector set, and then the mixed term, which was minus 2 y transpose A times matrix A plus B in brackets inverse times B plus set. And the last argument, in order to finally simplify it, is that we can change A and B here. So A and B are changeable, and this is by the same argument that these two are symmetric. So in essence, this would mean that we would have a matrix A here and a matrix B here. And then we see, well, this is essentially the same in all of these terms here. And if you now think in terms of, or if you bracket it like this, then you see that we just have a quadratic form which we can simplify into standard form. This quadratic form is given as, maybe it's not as obvious yet, but if I give it to you, then you will probably see it. It is given as y minus z, or vector y minus vector z, transpose, and then the matrix is A times A plus B in brackets inverse times B, closing brackets, times y vector minus z vector. That is already a good solution to our e prime. Recall, we are still in completion of the square, but we can simplify it even further. And for this, we will use the Woodbury matrix identity. If you haven't heard of this, that's not a big deal. We will just use it in this context here, and it allows us to find an expression for the summation of two matrices in brackets inverse. And it is given more generally, but we will use a simplified version here, and it is A plus B in brackets inverse will be given as A inverse minus A inverse times A inverse plus B inverse in brackets inverse times A inverse. These are a lot of inverses, and this could seem like it makes it more difficult, but what we have now here is a way in order to further simplify the amount of matrices involved in here. Because we now found a way in order to express the summation of two matrices in brackets inverse by the sum of their inverses. Let us plug this result into our general expression, still for the e prime, and for this we are getting y minus z in brackets transpose times matrix A times, and then the Woodbury identity, which is A inverse minus A inverse in brackets A inverse plus B inverse in brackets inverse, A inverse, and then we have the B, and then in brackets y minus z, and then let's multiply it out. So we are keeping y minus z transpose, and we're getting A times A inverse times B, and for this term we have minus A times A inverse, and then the summation of the inverse is inverse. It is A inverse plus B inverse inverse, and then we multiply with A inverse times B, and again, as said, a lot of inverses. And here we now see that A times A inverse cancels, it's the identity, and the same is here, it is also the identity. Then we are left with this expression here, and we will use another artificial identity, which we will be multiplying in here. So we have the artificial identity, and we will use this term multiplied with its inverse, and the inverse of the inverse is just the regular expression. So we will be using A inverse plus B inverse in brackets inverse times A inverse plus B inverse. Okay, I hope you see this. This times this will just be the identity matrix. Okay, then let's plug it in, and then we have y minus z transpose times in brackets A inverse plus B inverse in brackets inverse times A inverse plus B inverse, and then we multiply with matrix B, and then we have minus, this was the identity, so we are left with this one here, which is A inverse plus B inverse in brackets inverse, and then this one here, which was A inverse B, and then closing brackets, and we have the vector term left, which is y minus z. Now we can factor out the A inverse plus B inverse in brackets inverse, and if we do this, then we get y minus z in brackets transpose, then opening brackets, and then we have A inverse plus B inverse in brackets inverse, and then opening brackets, and then we are getting this term here, which is A plus B, both of them are inverse, and multiply this with B, and then minus A inverse B. And then we multiply, well, there should be more closing brackets, one more, right? So then we have y minus z here. And then if we multiply this out, then we are getting A inverse times B minus A inverse B will cancel. And B inverse times B will just be the identity. And then we can break this down further, and we are getting y vector minus z vector transpose times A inverse plus B inverse in brackets inverse times y minus z. And that was a long journey, but now, trust me, no further simplifications, and we arrived at our final expression for the e prime, and this was all just for the completion of the square. But why did we do this? Because we now only have 2 times the matrix in here. Of course, we have to invert A, we have to invert B, and we have to invert the sum of the 2 inverses, but this can be helpful for further applications of it. Okay, let's bring together what we have, and recall our normal form was given, so I would just think that this is the equation coming from before completing of the square. So we have f of vector x is given as x minus d prime in brackets transpose times a prime times x minus d prime plus our e prime, the scalar e prime. And we found all of them. We found d prime, we found a prime, and we found e prime. Let's plug them in. So we have x minus, let's look up what we had for the d, which was way up, all the way here. And we found this expression, so let's put this in. A plus b in brackets inverse times a y plus b z, then closing brackets, and then we have a prime was given as a plus b of our original problem, then multiplied with x minus, and then the same thing again, a plus b in brackets inverse times a times y plus bz. And then we have our e prime that we just found, which was the y minus z in brackets transpose multiplied by a plus b, both of them are inverted, then in brackets inverse times y minus z. And this is our completed square format of the quadratic form that we are given. And recall what was the original problem. So this was the original problem was the sum of 2 quadratic forms, and it was given as x minus y in brackets transpose times a matrix A times x minus y plus an x minus z in brackets transpose times the matrix B times an x minus z. And we wanted to bring it in the form of an x minus d in brackets transpose matrix C times x minus d plus an e. And then we can find these coefficients. We first have the C, which is this matrix here. Then we have the vector d, which we can find in 2 spots here. And we have the scalar e, which is this one here. And then we see the matrix C is given as A plus B. This will be our first result. And the D and the E will actually be similar to the D and the E prime from our completion of the square. But just for the sake of being rigorous, we will write it down once again. So we will be getting for the vector D the expression that we have here, which is A plus b in brackets inverse times ay plus bz, which will be this result. And for the e, we will be having what we just derived with the really long simplifications, and we are having the x minus y in brackets transpose of a inverse plus b inverse in brackets inverse of x minus y. And this will be our last result. But just to be fair, I will also include the other one, which wasn't as simplified as this one, which can also be helpful in certain scenarios. So let's say equivalently, we can write E is x minus y in brackets transpose of A times matrix A plus matrix B in brackets inverse times the matrix B times x minus y in brackets. And I would encourage you to take a look at the similarities between the univariate and the multivariate case. For the multivariate, it was quite a complicated derivation, but which was mostly due to the fact that we did some simplifications, which are not necessary in order to get a closed form solution, but will be helpful for simplifying computation, either in analytical cases or when working with computers. I will omit the example for the multivariate case, and I will produce an additional video which will be just an example for the multivariate case, so stay tuned for this. With this information, I'm at the end of the video. I hope you enjoyed the derivation. It was clear. If there's anything that is still missing, then please leave a comment. I would be happy to answer it. If you enjoyed the video, then please leave a like and a subscription. I would extremely appreciate this. Here you will now see similar videos. I hope to see you next time.